Okay, we have defined for any distribution, let's say for f(x) of x, if you have any distribution, we defined mean of this random variable, mean of x or mean of any function of that, okay, as integral of the value this function can take, g of x and x from minus infinity to plus infinity dx, which is basically the product of these two functions, the function here and this one. So this is the expected value of a function of your random variable. Sometimes we call it a statistic of this random variable. Now, in this chapter, we have defined the conditional Pdf. So instead of this one, you could use a conditional distribution. So you could use fx given y, which means that assuming that this y is equal to this real number, so you will have a function which is expressed in terms of x and y, and then you put it here. So obviously this function will be a function of y. Okay, so the expected value is a generalization of what we had. The only difference here is that I put another distribution which has a parameter y, but y here is fixed. So this is a fixed parameter. So let's go to details. So this is the outline of this chapter. So we are covering the conditional expected values, and then we'll have some engineering applications. So we talk about estimation theory and we talk about reliability, which are not the main component of this course, but you would need them in order to use. So conditional expected value for any function of a random variable, provided that I have distribution of these, because here I put condition given an event, so then I have to use the Pdf of y given the event n. So, and then this distribution is different with f y of y. So this is unconditional Pdf, but this is the conditional Pdf. Obviously, if this m has some parameters, these parameters appear here, and then they will appear here. So this guy is going to be a function of parameters involved in m. So if this event m is that we know a precise value of x, for instance, this x could be some observation you have about the value of some stock market at present, and this g of y is a function of price of another stock market or a bond or something. So in that case, instead of d for this distribution, you have to put the conditional Pdf of y given x. And this is just the definition. So you perform the integral and then you have the conditional expected value of what a statistic of one random variable given that. One example is that this g of y is y itself, so you will get conditional mean of y given value of x. Sometimes we abbreviate this one, or sometimes we could denote mu of y given x equal x, whatever is not confusing for people involved. We can simplify the notation. So we do have some simplified notations that could be used. Similarly, the variance of y given x is equal to obviously mean of y to the power 2 given x equal x, and then minus mean of y given x equal x to the power of 2. So you can use that. Or you could say that mean of y minus conditional mean to the power of 2, and then you perform the integral. So remember that this guy itself is equal to mu y given this guy itself here is given by this previous integral. So we first need to calculate this integral and then put it in the second one. let us have one example for that. Suppose that two random variables have jointly normal distribution. In that case, so what we get is mean of y given x, which is defined, which is denoted like that. Remember that this is a abbreviation that we just use it to that. I prefer to use this one, but sometimes it takes less time or it's quicker to use this one. So obviously we have shown that this is equal to mu y, and then a constant times the difference. This is the observed value for the x. For x, and this is the deviation of the observed value from the mean. So what we see is that the conditional mean after knowledge of x will become equal to the previous knowledge of y, which we had it in the absence of knowledge of x, plus a correction term. And this correction term is a constant factor of the deviation of what we observe from what we expect prior to the knowledge of x. So if you plot this function in terms of expected value of y in terms of x, you see that this is a linear coefficient, is a linear function plus a constant. So in the absence of x or y, we expect to be here in the absence of knowledge of x equal x. But as x is observed, if you have some deviation, for instance, let's say if x is here, so then you will have some correction on what we expect for y. So obviously you see that this is a linear estimator. It happens this to be optimal linear estimator for y given x, and also optimal nonlinear estimator. So you see that the correlation coefficient, so this sigma y and divided by sigma x, this is normalizing the deviation over the standard deviation of x, and is multiplying it to the standard deviation of y, and then multiplied by correlation coefficient. If this correlation coefficient is 0, then the knowledge of x will have no impact on what we expect about y. Similarly, we could define any other joint statistic of x and y given x. So this is going to be equal to the product of the value that this function takes times the PDF, which is characterized by this. So this is the PDF of y given x equal x. Because if you know x, the value of x, you cannot put the joint distribution here. You have to put the conditional distribution. So always the expected value is the value you take times the distribution that you have about your random variables. And here, because the value of x is known, only y is not known, so you have to use the conditional distribution.